Hello, everyone. Welcome back. Today we're going to be doing day one for our final unit of the course. And today specifically, we're going to be talking about continuous probability distributions. So here it says probabilities within a range can be computed by calculating the area under the probability distribution function, often a curve. The total area under a probability distribution is 1. Now, what is the difference between continuous versus discrete probability distributions? Well, discrete distributions involve gaps or jumps between the values, right? So, for example, if we're counting the number of people in a country, right? We can't have 5.5 people in a country. It doesn't work like that. Not just because that's a small number of people, but because we can't have half a person, or we can't have a million point 3, 4, 5, 6, 7 one people in a country, right? That we either have 1 or 0 or 2 or 3 or 4, or any number like that, but it has to be a positive whole number, right? Or zero, I guess technically maybe there could be a country where nobody lives there, but regardless, we can't have numbers between those numbers, and we also can't have negative answers, right? But mainly because there's gaps, right? There's gaps or jumps between the values for discrete random variables for that reason. Another example is if I'm counting the number of apples on a tree, right? There's going to be gaps, right? Maybe there's 0 apples or 1 or 2 or 3 or 4 or any number, but not any real number necessarily, right? Any number in terms of any whole number value, but not any number in the sense of we can't have like 3.578 apples, right? That, do we have 3 or do we have 4? So, which is it, right? Good. And so with continuous random variables, we don't really have gaps with numbers between the numbers. It really has to do with how good our measuring tool is to find the answer. So, for instance, if we're measuring somebody's height, well, it's true that we'll probably round someone's height to the nearest foot and inch measure, right? I'm 5'1", but am I actually exactly 5'1"? Well, probably not. Probably not. If I had a better measuring tool, maybe it's slightly more than that. Maybe it's slightly less than that, right? It's somewhere around there, but no two people are actually the same height because it really all just depends on how good of a measuring tool we happen to have and what we round to. But it is possible for someone to be, a height of 5.1247892 4, inches, right? That is possible, right? That's a possible height for someone. Or same with weight, for instance, right? Our scale just rounds to the nearest. When we stand on our scale just kind of rounds to the nearest pound or the nearest kilogram, whichever one you like to measure in. However, there are many, many more numbers on the scale. If we had a more accurate scale, it would probably tell us exactly how much we weigh, right? It's probably not exactly some whole number. It's probably that whole number point, blah, 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 if we really went into it. But the scales we use in day-to-day life, we don't really care about all those numbers. We mostly just care about the whole number representation is going to tell us, the rounded representation, that whole number is going to tell us something good enough, right? Same thing with kitchen scales to some degree as well. Actually, I think that might be a better example because with kitchen scales, people might care a little bit more about getting, more accurate decimals. However, even then, even with a kitchen scale, we're not going to get all the decimals. Like, we're not going to get a never-ending decimal that goes on forever, right? There's only going to be a kitchen scale that tells us so much. And so, in terms of weight, it just depends. It's a continuous random variable, right? There's no possible weight between 1 and 5 that wouldn't be possible to get, right? If we put just the right amount of sugar grains on there, because each sugar grain, weighs practically nothing, right? Very little, right? And so that's the way it is, right? Good. Okay, so let's talk about probabilities in the uniform distribution once again. I want to review that. It says here probabilities of the uniform distribution, as a reminder, n is the number of possible outcomes, and every outcome is equally likely to happen. So here's an example with continuous. Example 1 says the waiting time for crossing the American and Canadian border on a Tuesday is found to evenly range between 35 and 55 minutes. What is the probability that to wait at the border will take less than 42 minutes? So in this case, this is a continuous random variable, right? Because in terms of time, yes, we think of it in terms of minutes and seconds, but technically there's all those little microseconds in there. As I'm talking, we're going past tons and tons of microseconds, right? There's no possible exact timestamp that couldn't be created, right? That wouldn't be possible. It's possible to have half a second or a quarter or at a millionth of a second, right? That would be extremely, extremely fast, yes, but it is a possible time frame we could have. And so being between 35 and 42 minutes, that doesn't mean that, oh, we're either 35 minutes exactly or 36 minutes exactly or 37, or that doesn't even mean, oh, we must be at least 35 minutes exactly or 35 and 1 second exactly, 35 and 2 minutes exactly. It's like, well, no, there's all the numbers, all those decimals between the numbers. There's an infinite many possibilities between 35 minutes exactly and 35 minutes 1 second, even though it doesn't feel like it because a second is so quick, it goes by so fast, right? But there is that possibility there in that sense. So yeah, okay. So let's talk about the probability of each minute. So let's imagine every minute has the same probability because it says the waiting time on a Tuesday is found to evenly range between 35 and 55 minutes. So what would we have to do then? If we want to know the probability that it will take less than 42 minutes, what we need to do is we need to do 1 over 55 minus 35, right? Because if this is even, and this is also even, we need to figure out, how much of the time, right? What area is this? How much of the time is there actually that we're spending here? And the answer is going to be 1 out of 20 for each minute, right? Probability of each minute is 1 out of 20. And so in this case, we want the probability that x is less than or equal to, or actually not less than or equal to, let's just say less than, not that it actually makes a difference, less than 42 would be the same as the probability that we're between 35 and 42. And that means that that's 7 minutes. We could be between minute 35 and 36, 36 and 37, 37 and 38, 39 and 40, 40 and 41, 40 and 42, right? And so there's 7 possibilities there, right? There's 7 minutes. And the probability of each minute is 1 over 20. So that means the answer is 7 over 20 would be our answer. So that's our probability that the wait at the border would take less than 42 minutes. Good. Now they're asking, what is the probability that the wait at the border will take more than 40 minutes? Well, we know that it's all the same time between it's all equal between 35 to 55. So if the probability it'll take more than 40 is from 40 up to 55, right? And we already established the probability of each minute is going to be 1 over 20, right? So the probability that it's x is greater than 40 minutes is the same as the probability that we're between 40 and 55, which is 15 minutes, right? So this is going to be 15 times 1 over 20, which is 15 over 20, which is not 1/4, 3/4, right? 3/4. And so that's going to be our answer. And also notice that corresponds with the area under our curve, right? We would have this area here, and this is going to be 3/4 of the total area we have, right? Or same with the other one, it would be 7/20ths of that area, right? Because each minute is equally likely to find that range sometime between minutes. So it's not about being exactly 35 minutes, 36, 37, 38, and so on. No, it's about those minutes, those seconds between the minutes and even the milliseconds between the minutes. It's about the times in between those times. And that's the big difference between something like this distribution and the distributions we did in the previous unit where they were all very discrete, right? We were drawing marbles and, oh, here's a marble or here's a card, you know. Here it's not like that. It's continuous because we're talking about time. Good. Okay, let's move on to some more examples. So let's talk more about continuous distributions here. Continuous distributions involve continuous data, which allows for fractional or decimal values of the random variable, which means there's no gaps, no jumps between the random variables. So some examples, as we talked about earlier, would be height, weight, distance. I'm going to write those things down. Height, weight, distance, time is a big one. Another one is temperature, right? You know, our temperature, our knowledge of the temperature is only as good as our understanding of it, right? It's only as good as what the weather app rounds it to, right? But technically, there are numbers between the numbers when it comes to a temperature, right? It's a scale, right? So that's the question to ask yourself: is it a scale? Is it a spectrum? Or is it a very black and white thing where we just have, 1, 2, 3, 4, 5, and in between numbers don't make any sense? That's a question you can ask yourself in order to understand. Okay, so an exponential distribution, it predicts the waiting times between consecutive events in any random sequence of events. And so the cumulative density for an exponential function is this: the probability that x is less than or equal to whatever x we're choosing is 1 minus e to the power of negative kx, where k is 1 over mu, and that's the number of the events per time unit. And we know e is just our base exponential, where e is roughly 2.71828, and so on. Very good. So we're going to use this. We're going to use this to do another question about continuous random variables. The example 2 says the owner of a subway determines that the average time it takes to serve a customer is 8 minutes. What is the probability that the time to serve a customer will take less than 6 minutes? And this is, by the way, something I should mention about this exponential distribution. It's also known as a Poisson distribution, aka Poisson distribution, just in case anyone has seen this before. And instead of K, some people use lambda. Some people use lambda. So just to let everyone know, and just in case you have seen this before and you actually do know this, but it's different, there, right? So exponential distribution is much like Poisson distribution. Good. All right. So what's the probability it will take less than 6 minutes? Well, let's think about this. The probability that it'll take less than 6 minutes is equal to 1 minus e. Uh, oh, 1 minus e to the negative. Let's see, the negative lambda, or k in this case, times x, which is 6 in this case. So let's figure out what is the k value, or lambda. Well, we know x is equal to 6. We know mu is equal to 8 because it says the average is 8 minutes. And so we know k is equal to 1 over mu, right? Or, lambda, it would say as well. So that's going to be 1 over 8. So therefore, 1 minus e to the negative 6 over 8, or 0.75, if we put that in decimals, is going to give us 1 minus 0.47, which is equal to 0.53. So therefore, the probability that it'll take less than 6 minutes to serve a customer is 0.53. Now, this might seem a bit of like a strange answer of, wait, I thought but I thought the average time it takes to serve a customer was 8 minutes. So, how can it be more than a 50% chance that it'll take less than 6 minutes? Well, that's because if we look at this distribution, if we look at this exponential distribution, we can see that there's a few wait times here at the end that are skewing everything up. So that's skewing the average up because there's a small chance that maybe Subway, one of their machines will break down and it'll take like 2 hours to get your sandwich, but that's probably not that likely to happen, right? I mean, they probably sooner give you like a coupon to come back next time or tell you to go to a different Subway if you live in a big city or something like that, right? But there's always that small chance that something could happen and it takes a really long time, or maybe they're really, really delayed that day for some reason. Maybe, they're down a staff member and so it's taking extra time that day, or who knows what, right? And so therefore, and so that's why it's actually it's more likely there's more space here slightly below the mean, right? This is more space than all this other space. And so it might seem weird or counterintuitive that the average time, that here we're asking about what's the probability it'll take less than the average, and in fact a couple minutes less than average, and it's more likely to happen than we would expect. Good. All right, so let's do another one here. This one says, what is the probability that the time to serve a customer will take more than 10 minutes? So this is away from the mean. This is higher than the mean, but also we want to know about more than 10, right? More than 10 minutes. So this one we're expecting to be a relatively low probability, certainly lower than 0.53 here, because as we can see, if we go past here, there's less here, right? There's less here than there is in the beginning for our Poisson distribution. Okay, so x is equal to 10, right? Because there's 10, we want to know, is it going to take more than 10 minutes? Then we have mu, which is 8. And so our k value is going to be 1 over 8, or our lambda, right? 1 over lambda, whichever we'd prefer. Okay. So here in this case, I'm actually going to use the indirect method. I'm first going to find out what is the probability that it's less than 10 minutes, which we're expecting to be a relatively high probability, certainly greater than 50%, because, we're certainly better than 0.53, right? 53%, because, we're taking everything that is less than 6 and also more things, right? Things between 6 and 10 as well. So there's going to be more room for probability there, right? And so that's going to be equal to 1 minus e to the negative 1.25, which is equal to 0.713. There we go. Okay. So if the probability of it being less than 10 minutes is 0.713, then that means the probability of it taking more than 10 minutes is 1 minus the probability that it takes less than 10 minutes. And that's going to be 1 minus 0.713, which is going to be equal to 0.287. And so that's our answer. That's our answer. There's about a 28.7% chance that it'll take more than 10 minutes for the customer to be served at a Subway. Well, according to this question. Now, you might be asking, hey, we missed something. We missed what happens if it's exactly 10 minutes. And here's the thing about with discrete random variables. If this was a discrete random variable, we would have got the answer wrong, and I would be saying, "Oh no, we got this completely off. We got to do the whole thing again. We got to add something to it." But this is a continuous random variable where every individual time, because since there's so many, there's infinitely possible times, essentially has a probability of 0. What's the probability that it'll be exactly 10 minutes? Well, essentially 0, right? It's essentially 0 for every single probability out there, for every single outcome out there when it comes to continuous random variables, because if we could write all the times, we'd never stop writing. And so it doesn't actually matter whether we're looking at less than or equal to or greater than or equal to in these cases, because there's essentially no cases where we get any specific value, right? We're not really going to have a sandwich take exactly 10 minutes. It'll either take slightly more or slightly less, but not exactly 10 minutes or any other specific value, for instance. All right. Well, yeah, so that is that. Very, very good. But yeah, big thing to remember is that when it comes to continuous random variables, the probability of any specific outcome is just zero, right? If I ask what's the probability that it'll take exactly 7.57893 minutes, zero, right? Very, or infinitely close to zero, in other words, not going to happen. So you can just say zero. All right, well, that is everything for today. Good work today, everyone, and I will see everybody back for the next class. Next class, we're going to be talking about normal distributions, and that's a very exciting class and also a really key class. So do make sure you're there for that. I would say this is a more important class than today's class, so make sure you're there for that. Good work today, everyone, and I will see you then for that class. Bye, everyone.